Okay, so hello and welcome. Today I'm going to talk to you about the Thousand Brains project and how the Thousand Brains project is reverse engineering the neocortex to revolutionize AI. So at a high level, the Thousand Brains theory is a theory of how the human neocortex works. And the Thousand Brains Project is our nonprofit organization focused on advancing and implementing the Thousand Brains theory. So what is the Thousand Brains Project? It is a nonprofit research company. It is an open source project, so everything is MIT licensed. It is funded by Jeff Hawkins and the Bill and Melinda Gates Foundation. It's building a new type of AI that is based on principles of the neocortex, made for sensorimotor applications, and it is a general system with all the capabilities of the neocortex. So in an attempt to highlight what brains are good at, here is some very high-level correlations. We have our calculators and computers that are good at numerical operations. We have deep learning LLMs with their large number of applications that you all know about. And then we have the Thousand Brains project for sensory motor learning and action. Note that sensory motor does not need to be physically embodied. So while it is great fit for robotics, an analogy of sensory motor can be applied to virtual systems and abstract spaces as well. For example, things like navigating the internet. So who am I? Why are you hearing from me? I'm a principal engineer on the project, which means that amongst other internal responsibilities, I work on the software of the Thousand Brains system. My focus is on enabling our researchers and on turning research into working software. However, I am not a researcher. So I want to highlight my not a researcher status to point out that while I've learned a lot about neuroscience being on the project, I am likely not the best person to answer all of your neuroscience questions. We call an implementation of the Thousand Brains theory a Thousand Brains system. So what does a Thousand Brains system look like? It is a system built on a few key principles that we're going to go over next. First, we have sensory motor learning. So learning in every intelligent species is a fundamentally sensory motor process. So a Thousand Brains system will be able to ingest a continuous stream of self-generated sensory and motor information, like a child experiences when playing with a new toy, exploring it with all its senses and building a model of the object. So the system actively interacts with the environment to obtain information it needs to learn or to perform a certain task. Active learning makes the system efficient and allows it to quickly adapt to new inputs. Next, we have reference frames. As the neocortex learns models of the world, how do the objects look and feel like, where are they, and how do they behave? These models are structured by reference frames. Each reference frame stores where things are relative to each other. They're not just a bag of features. And these structures representations make it possible to perform necessary tasks for survival quickly, such as path integration and planning. Modularity, this is where the name of the Thousand Brains comes from. So the neocortex is remarkably similar everywhere. It is composed of general, repeatable functional units called cortical columns that learn models determined by their input. Each cortical column implements a general purpose algorithm for modeling sensory motor data, allowing for local, fast, associative learning. Each cortical column can model complete objects. And each cortical column can know about many objects, and no column can know about all objects. It is worth highlighting how small an input into a cortical column is. So to conceptualize this a bit, imagine looking at a world through a straw. So for example, in the visual system, the right and left visual fields are separated. In the eye, on the retina, there are blood vessels everywhere. The optic nerve makes a big hole we don't notice, and then eventually input ends up in V1 in the striate cortex. So the neurons in the V1 area have small receptive fields. When looking at a screen, a V1 neuron sees less than 1 centimeter. So that is the input into a cortical column, yet we still see things. So the combination of small receptive field and saccades occurring 3 to 4 times per second allow each cortical column to recognize things, even though it is like looking through a straw. All of these cortical columns need to communicate with each other and with the motor system. These communications must contain certain information for the system and the brain to work. And we represent this communication using the cortical messaging protocol. All of these key principles put together, sensorimotor learning, reference frames, modularity, and cortical messaging protocol, guide the project's research direction and our implementation choices. What is important to highlight here is that we do not intend to build exact biological replicas. The systems we build, as long as they abide by these principles, will reproduce the functionality of the neocortex. So, following these principles, what sort of system are we building? Here's a conceptual architecture overview so you can identify the system components involved and how they interact together. So in this diagram, the square icons represent the learning modules. The rounded at the top icons represent sensor modules, and the trapezoid represents the motor system. A learning module is our abstraction and implementation of a cortical column. A sensor module is our abstraction and implementation of sensory data being converted into CMP, the cortical messaging protocol. The motor system is our abstraction and implementation of the motor system. The solid lines depict communication via the CMP, the cortical messaging protocol. So let's highlight a few important elements of CMP depicted here. Pose is what we call the location and orientation and common reference frame. Features are what you may usually consider a feature, example, color, curvature, luminosity, etc. And then there are other auxiliary parts like confidence, sender ID, that sort of thing. These are the solid arrows. The dashed arrows are sensor-specific communication protocols that are not CMP. So let's say the eye sensor here made an observation. It will send this to the sensor module via the dashed sensor-specific communication protocol. The sensor module then sends the observed state to the learning module via the CMP. The learning module sends hypothesized state to other learning modules in the hierarchy via the CMP. The learning modules vote on possible states with other peer learning modules via the CMP. And the learning module sends goal state to the motor system via the CMP. Again, this is intended to illustrate the main system components, but we can arrange these in multiple ways. For example, we can link together multiple senses in a multimodal configuration so that these learning modules connected to LiDAR on the left and vision on the right can collaborate on what they are sensing together. By introducing hierarchy, we can model compositional objects. So in this setup, one learning module's hypothesized state output will become input for a learning module higher in the hierarchy. And we can extend and scale these arrangements. So here we have 4 touch modules and 4 vision modules arranged to vote together in a hierarchy under a set of higher level modules. Not depicted, but also possible are skip connections, hierarchical separations, and any other setups you can think of. Now let's go over sensor modules, and I'll explain details of learning modules next. So each sensor module sees a small part of the object that can move. So from the 2 illustrations here, the illustration on the right is what the sensor module actually sees. The viewfinder on the left is there to give you the context and help orient you as to what the sensor module is doing. The sensor module itself only sees the patch on the right. This is its view of the world through a straw. As mentioned before, the sensor module turns raw data into the cortical messaging protocol. So for example, an RGBD camera sensor will turn a patch into a point cloud in XYZ coordinates, extract pose and features and curvature, and send those via the CMP. So now let's talk about a bit about learning modules. And again, learning modules are based on cortical columns and model the incoming stream of poses and features using reference frames. This is sensorimotor integration. So for context, depicted on the right here is a schema of a cortical column. Now, the height of a cortical column is about 2.5 millimeters, and surface is about 1 by 1 millimeter. So in essence, it's about the size of a grain of rice. A cortical column contains many different neuron types and that are organized into layers. And this layer organization is found all over the cortex, and the structure everywhere is remarkably similar. There are about 150,000 columns, and each column contains 100,000 neurons and 500 million synapses. So understanding cortical columns is the key to understanding intelligence. Our implementation of learning modules maps nicely onto what we hypothesize happens in each cortical column based on the findings from neuroanatomy and physiology. Since learning modules are the key, let's go into the details of our latest evidence-based learning module. So a sensor module via CMP, the cortical messaging protocol, sends displacement and features and poses and attributes at locations to the learning module. Then the learning module outputs CMP to the motor system to perform movement. So this basic loop happens at each time step t. The learning module receives displacements and features and poses, and then outputs motor movement. Internally to the learning module, the displacement combined with features and poses at locations is enough information for the learning module to start to hypothesize whether the inputs correspond to any of the objects it already knows about. And the learning module then assigns an object ID and pose to the series of displacements and features and poses at locations it receives. The object ID and object pose essentially summarize the stream of input received from the sensor module. Then the learning module via CMP sends the object pose and ID to a higher level learning module in the hierarchy. And then while deciding what object it is observing, the learning module sends and receives votes from its peer learning modules that allow it to rapidly and as quickly as one shot decide on an object being observed. And then lastly, to determine the motor output, the learning module comes up with a goal state, encodes it in CMP, and transmits that to the motor system. So to help visualize what is going on, here is a step-by-step animation of a single learning module going through the loop and recognizing between 4 different objects it knows about. So the current hypothesis inside the learning module are depicted as point clouds on the bottom of the slide here. The red points are the accumulated evidence based on the observed patch input and movement. And then, as you can see, evidence is accumulating on the mug. And then once enough observations are gathered, you can see the evidence accumulate. Excuse me, you can see that the object has been detected. In the upper left, the displacement and the pose feature kind of traces a path of how the sensor is looking at the actual object. Again, the viewfinder is just for you. The learning module only sees what the sensor patch is sending across. Here is a similar example with a different object. And in this case, the object is dice. And as below, you can see evidence accumulating on recognizing the dice on the below. Again, the viewfinder is just for you, and it's always interesting to see the sensor patch and how the learning module actually learns the object from that particular point of view. Here is a visualization of how voting helps to rapidly decide on an object. So again, the viewfinder in the upper left corner is only for your context. The learning modules only see their corresponding patches. So even though all patches see a different part of the object across all 5 of them, there is a rapidly vanishing small number of objects that could match observations of each learning module. It is the difference between you closing your eyes and trying to identify a cup with the tip of one finger versus grabbing the cup with your entire hand. Only the shape of the cup can explain the configuration and sensation of all of your fingers in that particular arrangement when you grab a cup. And this is what makes voting such a powerful mechanism. And then lastly, a bit about the motor system and decision making. It is important to remember that every learning module is sensorimotor, in that every learning module, everywhere in the architecture, outputs motor projections. So they come from layer 5 over here. You may have heard of the motor cortex in the brain. However, neuroanatomically, every part of the neocortex outputs motor projections to the body, not just the motor cortex. So it is worth repeating, every learning module in the system outputs motor commands. As to what motor actions the learning module outputs, that is decided based on the state of the world and by the policies active within the learning module. We made the most progress on inference policies. We are working on learning policies, and manipulation policies are future work. We think of policies in 2 modes, model-free and model-based. A model-free policy does not involve the learning module. So I enriched this overview diagram to include the CMP message from sensor module directly to the motor system. Neuroanatomically, motor-free policies correspond to subcortical circuits. That is, you do not need the neocortex involved to execute a model-free policy. So here's an example of a model-free policy. While neuroanatomically inspired, we can have just generally helpful model-free policies. So we can have an if you follow the object, return to the object policy without involving any learning modules. This can be done inside sensor module and motor system loop. Similarly, we can have a policy that follows curves without involving the learning modules. So there is enough data in the sensor module to follow curvature without models. As for model-based policies, these are the ones that leverage the models learned in the learning modules. So think about typing a word on a keyboard. Your learning modules send motor commands for words to appear. Other learning modules tell fingers to move, and some model-free policies execute the learned fine motor behavior movement required for familiar keystrokes. So a highlight here is that a model-based policy can recruit model-free policies for their work. We also have some model-based policies that don't rely on specific instances of models. For example, guiding explorations to places on an object that will provide the most information to distinguish between current most likely hypotheses. We can test rotational symmetry. We can test object boundaries by expecting absence of an object if we move off of it. And here is an example of a model-free and model-based policies in action together. We start off with a model-free exploration following the object curvature. Then, to disambiguate, we use a model-based policy test to jump to a location where we will gather the most disambiguating data. So if you have a fork, a knife, and a spoon, and you touch the handle, then you may want to check the other end of the utensil to quickly determine which one of these it is. Okay, so what can the system do today? As mentioned briefly before, our current focus has been on object and pose recognition. Our experimental setups consist of learning and detecting objects at poses. So we divide our experiments into epochs, episodes, and steps, and then allow the system to learn and then match and update its learned objects. We also maintain a list of benchmarks related to this research goal. So with that context, here's what the system can do. It learns from very little data. You don't have to provide tons of images. Objects can be learned with very few data points. The system requires little to no supervision. It learns continuously without catastrophic forgetting. If it recognizes a known object, it can switch to exploration mode and create a more detailed model to aid future recognition. The system can recognize objects and their poses, and the objects can have unseen before points. They can be in novel orientations and locations. They can be noisy or partially obscured. We implemented sensors that are analogous to vision and touch, and the system demonstrates cross-modality transfer. That is, if we learn an object via our touch sensor, then we can recognize it with vision and vice versa. The system also generalizes based on shapes. The model-free and model-based policies aid in a more efficient learning and recognition. It allows us to efficiently move across an object to recognize it faster. Lastly, the system uses significantly less compute than deep learning systems. So that's it. That's the high-level overview. There is a lot more to learn and understand, and you can find us at thousandbrains.org. We have a YouTube channel where we post lots of research meetings. Our code is MIT licensed and open sourced on GitHub. We have extensive documentation. We have a discourse forum where you can talk to us, as well as a reading list of papers and publications. If you found this interesting, we are looking to integrate with robotics APIs, and we could definitely use your help. Thank you very much. And are there any questions?
All right, thanks so much. Sounds great. Thank you. Yeah, I do have some questions. So you mentioned there's like some kind of like cortical columns, right?
Yes.
And then you mentioned those cortical columns have neurons. Like, how do you like emulate or simulate those in this case? Is like, do you still use like some kind of neural nets, or how do you simulate those, or how you go about it?
Yep. So I'm trying to organize trying to give you a short answer. So I've highlighted before where we do not need to implement exact biological replicas of the neurons. So for example, for this evidence learning modules, what we have, and then as long as we follow the principles that we learn from how the actual cortical columns in the brain work, as long as we follow those principles, we can build it using whatever technology that we have available. So kind of think we want to do flight, we don't need to build birds, we can build airplanes. That sort of kind of analogy. And so what we have here is for the evidence learning module, it's a XYZ Cartesian coordinates. Those little hypotheses are point clouds in XYZ, and we just store them in memory. And as you moving the sensors, we try different orientations to see if the object fits and helps it recognize. But by doing that and by incorporating the voting, you rapidly reduce the number of hypotheses that you have to test, and it becomes a very efficient object recognition mechanism. But so the general approach of the project is understand the underlying neuroscience and how the brain does this, and then extract the principles so that we know whether we're losing something or not by changing technology and not emulating neurons, but instead of going to like XYZ coordinates or other things. So does that answer?
Yeah, I think so. Yeah, yeah. I'll dig more. It's very interesting. But
Yeah. So if you look in our code, you'll see a lot of like tensor operations and vector rotations
got
and
it,
that sort of things. You will not see much neural networks in there.
got it. Yeah,
Actually, I don't think you'll see any neural networks in our code right now.
got it. Yeah, yeah. That makes sense.
And now I want to highlight that doesn't mean that neural networks will not be useful. The XYZ coordinates and kind of imagining vectors and how the objects are recognized are helpful for everybody to understand as a first go, right? So the evidence learning module uses more humanly understandable concepts. But if we find that neural nets or other pieces can do that particular piece better inside a learning module, then we can use whatever works the best.
Got it. So, like, how long have you been working on this? Is this something like a many-year kind of project, or is it?
I think Jeff Hawkins has been working for this for over 2 decades on the research
Wow.
project. So there is a long history of um, Jeff Hawkins, the Redwood Neuroscience Institute in Berkeley, then a commercial company, Numenta, and now the Thousand Brains Project in January spun out of the Numenta commercial company as a nonprofit in order to pursue this research and the theory in the open, and so
Yeah,
that
yeah,
everybody can benefit from it.
yeah. I have definitely heard of Numenta. Yeah, that sounds
But
very familiar.
so if you've heard of Numenta and their open source project, this is Thousand Brains project now.
All right. Oh, cool.
And
Yeah,
so there's a long lineage of things. So for people who have done explored Numenta before, there are some very neuro-inspired algorithms like HTM and SDRs and sparsity and temporal pooling and spatial pooling. Those are essentially a toolbox that we can use in order to apply it to the appropriate places in the Thousand Brains theory. So there's a long lineage and decades of research on this.
wow. Yeah, yeah. It's be interesting. Like, so, like, as far like object detection. Sorry, I keep asking all the questions. So if somebody else has more questions. So, it's like, how successful were you with that? Like how long does it take, for example, to go from, I don't know, like, do you have like a big database of objects, and then you just show, I don't understand exactly all the process, but what, like, how does the process look like to make it detect these objects?
Right. So we have so we use so a best way to think about and the code, we call it Monty. It's named after Vernon Mountcastle, who's the neuroscientist that wrote up and postulated that cortical columns exist. And so you hear me say Monty, that's the name of our code base. So the way we have Monty set up is the closest framework you can think about is like reinforcement learning. So we have a simulator, we have Monty, and then Monty controls what we call agents, but essentially they're sensors inside the simulator. And so you have the loop of move the sensor, report what the sensor sees, that goes to the Monty learning modules that generate new motor behavior, move the sensor, report what the Monty sees, etc. So the way we set up our experiments, we load an object into a simulator and then loop through, let the sensor look at the object from different places. If it's a touch sensor, it will get right up on the object and kind of trace it out in space. And
I
based
see.
on that, it can learn what the object is. That's the kind of nice trick about the sensorimotor learning, and what makes it so efficient is because you can move your sensor in the world, the system knows its movement. And so by that, it can infer like the sizes of things out there in the world, right? Like if you have a finger that's tracing a cup,
Yeah.
your brain knows how far it needs to move to make a cup. So internally, it can make a model of how far things are because of how you're moving your sensor. If you never have movement and you never move your sensors, then that becomes a much more difficult problem to infer.
So that's what we saw on the little window there when it was like moving around. That's the sensor moving around. Like you had like two little boxes, one of the actual object, but then there was another one with a small red.
Yeah,
Yeah, somewhere all the way back in the beginning. Yeah, yeah,
yeah,
like
like this
right
thing.
this one. Yeah, yeah, yeah. So like sensor patch, so it keeps moving around. That's what it does. That's
Yeah, that's exactly what it does. So these are actually the viewfinder and the sensor patch are
Mhm.
essentially what the sensor. This is the visual sensor. So what it sees in the simulation. So we
Yeah,
loaded an
yeah.
object into the simulation. This is a simulator, and now the
Mhm.
sensor is moving, kind of looking at the object. Actually, this will probably be a touch sensor because
Mhm.
it's moving all over the place. And so it will just trace out the shape, and because of that, it's very efficient to figure out the dimensions of the objects
Mhm.
because you are controlling your movement. So you can infer what the object's dimensions are and what shapes it's fitting.
Oh, yeah, that's pretty cool. Yeah, I'm gonna start with my questions. Somebody else, maybe, maybe somebody else might have some questions.
I have a question. You may have already mentioned this, and I probably didn't catch it, but what are some of the best use cases for this type of technology?
Yeah, the higher level questions. The So robotics is for sure one. So
Okay.
anything where you're moving in the world, because again, one is for you to learn effectively, but also to interact with the world. You kind of almost want embodiment. So what this will be helpful for is, like, let's say, imagine you have. I'm assuming everybody heard of Boston Robotics, or
Yes.
where you have the so if you have a Monty, you essentially strap a neocortex onto a robotic system. Like Monty will not learn doesn't need to learn the fine level movements, etc. Monty can just using the cortical messaging protocol can send like the goal state and like some we tend to refer to as subcortical, but whatever fine grained control robotic system that already exists will just execute that desired end state. So Monty is sort of the neocortex that you can put on any existing robot that already knows how to move or how to place itself, because we would just say that's subcortical, that's like you maintaining your balance, that sort of thing. And Monty can actually give you control over this. Now, I've been very literal about current capabilities and object recognition and that sort of thing because I wanted to keep this as grounded as possible. But the other applications of this system are, as you build up the hierarchy of learning modules, essentially higher level learning modules will get input from lower level learning modules. We have we have theories, and we know how like conceptualizing behaviors will work. So you can learn behaviors, you can learn abstract knowledge. All of that is sensory motor, like this sensory motor algorithm that we're using to recognize these objects, to cause movement and happen and movement to happen. You can translate to abstract space, and we can model higher level concepts using the same thing. There's a movement in an abstract space happening. You can get the shape of a concept by moving around it. That's a little more future research, but we already have kind of the pathway to get there. So um, the reason I'm highlighting that is because in the future, this will be the system that can do continuous learning like a human can, where you can enter an environment, you can be pre-trained on certain things, but you can then interact with the world and update your uh, kind of immediate learning modules that deal with ground reality of like, oh, there are new objects here, I'm going to learn what these objects are, etc. But you can also update your higher level concepts of knowing what kind of goal you want to achieve, understanding the situation, understanding the room, that sort of thing. So eventually these will become, AGI will come from this type of model. It will not come from the deep learning type of model. That's what we believe. There was one more application, and then kind of intermediate level of application. So there is a this is a good example because it's so different. So there is there are mobile ultrasound machines that you can hold in your hand, and there is a need to be able to in remote areas in the world where you do not have enough people trained in ultrasound and other things, and so you need a trained technician to do ultrasound to diagnose anything that happens in your body. But with a system like Monty, what you can do is you can have a hybrid where Monty can direct a human to move in a specific way because it's a sensory motor system. It can understand what it's trying to recognize. It can implement its policies of trying to disambiguate and diagnose something specific, and then it can direct a human to move the ultrasound in a specific way. And then it'll get more data and move ultrasound in a specific way, and then work towards diagnosing things or clearing somebody. And so that this sort of sensory motor interaction also allows you for hybrid solutions where Monty can work with humans, where humans can provide the motor part of it, and Monty can provide like an expert sensory aspect of it. So there's also this hybrid type of solution.
Okay. Awesome.
So you said that is learning continuously. Like, can you maybe, I don't know if you have a easier explanation for that, or like
so yeah. So what we mean by continuous learning is first, if you've never come across an object before, then when Monty looks at it or perceives it, then it will have no hypothesis of what it is. So it can decide this is a new thing I've never seen before, and then it's just going to assign random identifier to it and then learn what that object is. Then if you take that object away and it comes back, it'll be like, hey, I have a thing, and like, oh, it's a thing that I learned just like a minute ago or something like that. Now, if it recognizes and it's confident that it's the same thing that it learned already before, it can spend more time of enriching its model, of like maybe paying attention to some details, etc., to become even more finely tuned to recognizing the specific thing. Maybe it will see a side that it hasn't seen before and be like, oh wow, there's a handle on this side, or something like that. And so the switch back and forth between recognizing and learning, it's very dynamic with Monty, and it's a tunable hyperparameter of how often you want to switch back and forth between. If you can turn off all learning, right? You can. It's a nice thing about it is it's an artificial system, so you can say thou shalt not learn anything, and it will just only recognize objects, or you can tell it everything is brand new, learn everything from scratch, and then the spectrum in between.
It's pretty cool, yeah. That's definitely different than what I accustomed with. So you, like when you have this simulator, so assuming like you have a robot, right? And of course you have to have some compute available. Like I'm thinking about like what kind of compute do you need for this? Like you say, do you have to have that simulator all the time, like running? Let's say you have like a physical robot, and you have to put a computer on it. Like what are the kind of the compute requirements for this? Is there since like you say you have some simulator, you have to keep the simulator in the robot? Yeah. Okay.
So Monty needs an environment to interact with. So the easiest way for us is to have a simulator, and that will simulate the environment. And you could do something along the lines of go into an environment and then record series of sensations and then play that back to Monty, as long as there's sufficient enough data of this is where the sensor was, this is how it moved. So a lot of data sets could be adapted as long as there's movement data in it. The problem is a lot of current data sets don't have that movement data, where your sensor went from, here's an image, and then if you move over, here's an image, and here's an image. A lot of data sets don't have the difference between the two. They're not formulated in that particular way. But if you had that data set, then you can essentially play back an experience to Monty, and it would learn whatever it could learn. But it might be limited because, well, so not limited in the sense of it might be less effective because Monty cannot decide to try out specific policies, right? Like if it's having trouble recognizing something, it might want to go look at a different way, and if you never recorded that path, then it might not get to see it. So the interaction is helpful. That was one part of the question. I think there was another one.
Yeah, like, I mean, the compute requirements.
The compute requirement.
Yeah.
It's compute. It requires so much less compute that we can emulate things on a CPU. we can run experiments without GPUs. GPUs make it go faster, but we're not restricted by GPU availability. So all our like benchmarks and stuff runs on CPUs.
Nice. So it can probably run on some like a few Raspberry Pis or.
It's now we're getting to the details of where the code is. Again, it's open source, so all the contributions are welcome. It does not run on Raspberry Pi because right now it's restricted to Mac OS and Linux x86 for a variety of reasons.
Got it.
Like for example, our simulator is Habitat Sim, and that does not run on Windows. It doesn't run on Raspberry Pi. So we've decoupled a lot of the code, but we still have more decoupling to do.
Got it. Cool. Pretty cool.
Yeah.
Any other questions in the audience?
What prompted me to talk at the robotics meetup is because this year we're working on integrating into a robotics API so that Monty can like ROS or something like that, so that we can instead of just being in a simulator, we can actually interact in the world. So that's one of our goals for this year.
Yep, it's pretty cool. All right. Cool. Well, thank you so much, Tristan. This was very interesting talk. Yeah, I'll stop the recording right now. All right. Cool.